Good day everyone. Welcome to my class again. This time we'll be discussing about accuracy, precision, and errors in measurement. By the way class, I am Mr. Muhammad Simpal, your physics teacher from Esperanza National High School, STEM Department. Before we proceed to the lesson proper, let us have to know the expected output. At the end of this video lesson, you are expected to obviously differentiate accuracy from precision and differentiate random errors from systematic errors. Now let's talk about accuracy. Now accuracy class is simply the closeness of the measurements to a specific value. And also it compares the measurement to the time value, and it refers to the correctness of course, the measurement when we say accuracy. An accurate measurement correctly reflects the size of that thing that being measured. In other words, class, when we talk about accuracy, we are referring to the closeness of the data gathered to the actual or the accepted value that underwent in the experimental procedures. So we have observation 1, 2, 3, 4. Observation 1, 2, 3, 4. Now, in terms of accuracy, let me ask you this one. For example, they have tasked to measure the length of a certain object. For example, they tasked to measure the certain length of an object, but the actual length of this one is, let us say, 17 centimeters. The actual length of that object. Now, these two scientists now have tasked to evaluate actual measurement of the object or verify the measurement of that object. For Susan, arrive at this data, 17 centimeters for observation number 1, 18.0 centimeters for observation number 2, 16.0 for observation number 3, and 15.0 centimeters for observation 4. While Ami have arrived at this data, 15.5 centimeters for observation number 1 and 15.0 centimeters for observation number 2, 15.2 centimeters for observation number 3, and 15.3 centimeters for observation number 4. If we go back to the definition, when we talk about accuracy, the closeness of the measurement to a specific value, it must be reflected on that observation. Going back to this one, this means in this part, Susan got the accurate result since Susan has this value from the first observation, which is 17.0 centimeters. That is exactly the same with the actual value of the object. And for Ami, although this value here, this data here are very close to each other, look at this one, 15.5, 15.0, 15.2, 15.3, but none of this data, okay, none of this measurement or value or observation reflects the actual value of the or actual length of the object, which is 17 centimeters. That is why in this case, Susan has more accurate measurement or observation than Ami. That's for accuracy. Now let's go to precision. Precision class is the closeness of the measurements to each other. Do not be confused on the first statement. For accuracy, closeness of the measurement to a specific value. And precision, closeness of the measurement to each other. For also, it is repeatable and reliable, meaning we're talking about consistency of the results and getting the same measurement at a time. And also, measurement can be precise but not accurate. Let us try to consider again. Let us go back to the sample that I have presented here. Now, accuracy. Let's go to precision. precision. Now let me ask you this one. Considering these results of the observation from these two scientists, which data or observation is more precise, knowing that the exact value is 17 centimeters? According to the definition of the precision, it must be, or it is the closeness of the measurement to each other. That means when we look at this data, we can simply deduce that the repeatable value here, as can be gleaned in this data or sample data, is obviously for AMI, because this results of measurement is very close. The difference is just a matter of point something, 15 point something, 15.0, 15 point centimeter. So they are very close. Now, for example, accuracy versus precision. For example, we have here a target board. Consider this one as target board, and let us say the first thrower got this section here, so he hit this one, for example, and the second thrower hits this part of the target board. Now, question, figure 1, figure A. This is figure B. Since they hit the second, they hit this one, this spot, for example, this spot here, it can be concluded that the figure 1, high precision. Why? Because I think I will have to repeat this one. I will have to redraw this. For example, this one, and that one. So this is the bullseye. So this is high precise. It's because although they didn't hit the eyeball of the target board, but they are very close. They hit the other area of the target board, but the result is very close. So the closeness of this one, of the heated area of this target board, represents high precision. In terms of figure B, this is, although they are very much separated, but they hit the bullseye of the target board. So we can say that the figure B has high accuracy. In terms of accuracy in figure A, this is, since they didn't hit the bullseye target, this is low accuracy. Obviously, because they didn't hit the bullseye target. Now, in terms of precision in figure B, this is also high precision, because they hit the bullseye target, and at the same time they're much closer to each other. So that's how we simply understand or explain accuracy and precision in terms of the diagram. I hope you can follow me and you will have an understanding later of what I'm talking here. Now we have types of errors that we'll be encountering in doing measurement. So the first one is systematic errors, or the determinate error. And the second one is random errors, or the determinate error. What is systematic errors? For systematic errors class, Usually, this is predictable, consistent departures from the true value due to problems with the calibration of your equipment, and this leads to the extra differences of your measurement. And obviously, the error is reproducible and can be discovered and corrected. So we have types of systematic errors, class. The first one is instrument errors. When we say instrument errors, basically, we commit systematic errors from instrument itself. Maybe we failed to calibrate it before using it to our laboratory experiment or our project. That is why we can address systematic errors first to instrument or failure to calibrate your instrument. Second one is method errors. If we have series of observations, particularly when doing a series of experiments, we commit methods of errors by simply maybe in sampling procedures. We have a lot of samples and we have committed a wrong sampling technique of that data, and method of errors will arise from that. The third one is personal errors, and this is solely addressed to your lack of judgment, because basically it's hard for us to conclude or judge based on what we have seen from instrument. Okay, those are the types of systematic errors that can be encountered and can also be solely addressed to systematic errors. For random errors is just a fluctuations around the true value as a result of difficulty of taking measurement, and basically this is always presented, or this is always present and cannot be eliminated in our observation. And that is why we are doing series of measurements. We cannot settle for only one measurement for that data to be concluded as a result of this experiment. Instead, sometimes we do 3 trials, 4 trials, or even higher than that, just for us to get the accurate result from that. So random errors is normal and always present and cannot be eliminated in our measurement. We have also a way of determining error. So for example, suppose that we have a thermometer and we measure the boiling point of water at the standard pressure, and usually we have for example, the thermometer reads the measurement with a value of 99.1 degrees Celsius, and basically we know that the actual boiling point of water is 100.0 degrees Celsius. So another way of determining error for this example is by knowing what is the accepted value, obviously, and what is the experimental value. And this is another way of determining error. For accepted value, obviously this is a correct value for measurement and based on reliable references. For example, the boiling point of water is 100 degrees Celsius. That is really a constant boiling point of water. We cannot change that easily. It's because it underwent thorough experimentations and trials just to conclude that the boiling point of water is 100, and it has been agreed by a scientist. So we cannot change that easily. That is why that is for accepted value, correct value for measurement based on reliable references such as the scientist or a physicist. Experimental value, obviously the value of measurement in the laboratory, or the actual value of measurement you have observed based on the procedures of your experimentation. For example, the accepted value of boiling point of water is 100 degrees Celsius, and your computed or your experimental value is let us say 99.1 degrees Celsius. For you to know the error of this measurement, you just simply do this one, error. Maybe can express mathematically. Error is equals to accepted value or the experimental accepted value minus experimental value. So we plug in the available value here for accepted value, that's 100 degrees Celsius, minus for experimental value, that's 99.1 degrees Celsius. To the operations, this gives you 0.9 degrees Celsius. This is your error of measurement. You can pause this video and copy this one. Now, another way of determining error is by percent error. What is percent error? Percent error class is simply the percent error of a measurement, or the absolute value of the measured experimental value minus the accepted value divided by the accepted value multiplied by 100%. If you want to know how many percent the error that may fall on your in your measurement, for example, you are very eager to know the percentage of error in your measurement. So we can do this one. We can express that mathematically. So according to this the definition of percent error, the percent error of measurement is the absolute value of the measured experimental value minus the accepted value divided by accepted value multiplied by 100%. So this is expressed by this one, percent error, or we can say percent error, something like that. So percent error is equals to, according to the definition, the percent error of measurement is the absolute value of measured experimental value. So absolute value of measured here is referring to experimental value. That is why we will put experimental, I will just put EV, experimental value, minus the accepted value, AV, absolute, divided by the, again, divided by the accepted value, again, absolute, times or multiplied by 100%. So this is the percent error formula in determining how many percent of error in your experiment or in your data, where EB here is the experimental value, and AV here is the accepted value, and percent error is also percent error. Now when we say absolute value, it is always positive. It is always presented as a positive value, and you multiply that into 100. So that's how we determine the percent error of our measurement or our laboratory results. You can pause the video and copy this one, because you cannot find this principal concepts in your module. Now, for example, let's proceed to the example on how are we going to find the percent error of the measurement applying this formula. Again, you can pause your video and copy this one. Now let's go back to our video. Slide. Let's go back to the determining error, and let's consider that example. Suppose you use the thermometer to measure the boiling point of water at a standard pressure. The thermometer reads 99.1 degrees Celsius. And you probably know that the true or accepted value of the boiling point of pure water at these conditions is actually 100 degrees Celsius. Let us add a statement in the problem. What is the percent error of the measurement? Now we are going to find the percent error of that measurement. So let's don't forget to list the given. Now what are the given? The boiling point of water is 100 degrees Celsius, and this 100 degrees Celsius now is the accepted value. So accepted value is 100 degrees Celsius. And the experimental value, according to the statement here, experimental value is 99.1 degrees. So experimental value is equals to 99.1 degrees Celsius. What is the percent error? Question mark. Let's go to our formula. Percent error is equals to accepted value minus experimental value, or let's try to review our measured experimental value. So this is experimental value minus accepted value divided by accepted value all in absolute value multiplied to 100%. Now substitute the value here. This is equals to experimental value is 99.1 degrees Celsius minus, this is the accepted value is 100 degrees Celsius divided by accepted value, which is 100 degrees Celsius absolute, times 100%. So 99.1 degrees Celsius minus 100 degrees Celsius is just an error. So you subtract that, the result becomes 0.9 degrees Celsius divided by 100 degrees Celsius times 100%. Now do the mathematics of that, still in absolute value. Do the mathematics of that. 0.9 degrees Celsius divided by 100 times 100%. The result becomes 0. Result is, you try to recheck this one in your calculator if you have a scientific calculator. So the result is 0.9%. So this 0.9% now is the answer for the percent error of this measurement. That would be all. If you have some clarifications regarding the topics today, you can chat directly to our group chat, and I will be happy to hear from you after this video. Thank you so much for your time. I hope you have learned something from it. See you in the next video. Keep safe, everyone.